physicists link two time crystals in seemingly impossible experiment. A new demonstration of these exotic constructs could help bridge classical and quantum physics. By Paul Sutter and Live Science. SACMA/Science Photo Library/Getty Images. Physicists have created a system of two connected time crystals, which are strange quantum systems that are stuck in an endless loop to which the normal laws of thermodynamics do not apply. By connecting two time crystals together, the physicists hope to use the technology to eventually build a new kind of quantum computer. It is a rare privilege to explore a completely novel phase of matter. Samali Adi, the lead scientist on the project from Lancaster University in the United Kingdom, told Live Science in an email. From crystal to time crystal. On supporting science journalism. If you're enjoying this article, consider supporting our award-winning journalism by subscribing. By purchasing a subscription, you are helping to ensure the future of impactful stories about the discoveries and ideas shaping our world today. We encounter normal crystals all the time in everyday life, from the ice in a cocktail to the diamonds in jewelry. While crystals are pretty, to a physicist they represent a breakdown of the normal symmetries of nature. The laws of physics are symmetric through space. That means that the fundamental equations of gravity or electromagnetism or quantum mechanics apply equally throughout the entirety of the volume of the universe. They also work in any direction. So, a laboratory experiment that is rotated 90 degrees should produce the same results, all else being equal, of course. But in a crystal, this gorgeous symmetry gets broken. The molecules of a crystal arrange themselves in a preferred direction, creating a repeating spatial structure. In the jargon of physicists, a crystal is a perfect example of spontaneous symmetry breaking. The fundamental laws of physics remain symmetric, but the arrangement of the molecules is not. In 2012, physicist Frank Wilczek, at the Massachusetts Institute of Technology, noticed that the laws of physics also have a time symmetry. That means any experiment repeated at a later time should produce the same result. Wilczek made an analogy to normal crystals, but in the dimension of time, dubbing this spontaneous symmetry breaking through time a time crystal. A few years later, physicists were able to finally build one. Quantum secrets. A time crystal keeps moving and repeats itself periodically in time in the absence of external encouragement, said Adi. This is possible because the time crystal is in its lowest energy state. The basic rules of quantum mechanics prevent the motion from becoming completely still, and so the time crystal remains stuck in its never-ending cycle. This means they are perpetual motion machines, and therefore impossible, remarked Adi. The laws of thermodynamics suggest that systems in equilibrium tend toward more entropy or disorder. A coffee cup sitting out will always cool, a pendulum will eventually stop swinging, and ball rolling on the ground eventually comes to rest. But a time crystal defies that, or simply ignores it, because the rules of thermodynamics don't seem to apply to it. Instead, time crystals are subject to quantum mechanics, the rules that govern the zoo of subatomic particles. In quantum physics, a perpetual motion machine is fine as long as we keep our eyes closed, and it must only start slowing down if we observe the motion, Adi said, referring to the fact that the exotic quantum mechanical states required for time crystals cannot keep operating once they interact with their environment, for example, if we observe them. This implies that physicists can't directly observe time crystals. The moment they try to watch one, the quantum rules that allow them to exist break down, and the time crystal grinds to a halt. And that concept extends beyond observation. Any strong enough interaction with the external environment that breaks down the quantum state of the time crystal will make it stop being a time crystal. This is where Adi's team came in, trying to find a way to interact with a quantum time crystal through classical observations. At the tiniest scale, quantum physics reigns. But bugs and cats and planets and black holes are better described by the deterministic rules of classical mechanics. The continuum from quantum physics to classical physics remains poorly understood. How one becomes the other is one of the outstanding mysteries of modern physics. Time crystals span a part of the interface between the two worlds. Perhaps we can learn how to remove the interface by studying time crystals in detail, said Audi. Magical magnons. In the new study, Audi and his team used magnons to build their time crystal. Magnons are quasiparticles, which emerge in the collective state of a group of atoms. In this case, the team of physicists took helium-3, a helium atom with 2 protons but only 1 neutron, and cooled it to within a 10,000th of a degree above absolute zero. At that temperature, the helium-3 transformed into a Bose-Einstein condensate, where all the atoms share a common quantum state and work in concert with each other. In that condensate, all the spins of the electrons in the helium-3 linked up and worked together, generating waves of magnetic energy, the magnons. These waves sloshed back and forth forever, making them a time crystal. Audi's team took 2 groups of magnons, each one operating as its own time crystal, and brought them close enough to influence each other. The combined system of magnons acted as one time crystal with 2 different states. Audi's team hopes that their experiments can clarify the relationship between quantum and classical physics. Their goal is to build time crystals that interact with their environments without the quantum states disintegrating, allowing the time crystal to keep running while it is used for something else. It wouldn't mean free energy. The motion associated with a time crystal doesn't have kinetic energy in the usual sense, but it could be used for quantum computing. Having 2 states is important because that is the basis for computation. In classical computer systems, the basic unit of information is a bit, which can take either a 0 or 1 state, while in quantum computing, each qubit can be in more than one place at the same time, allowing for much more computing power. This could mean that time crystals can be used as a building block for quantum devices that work also outside the laboratory. In such a venture, the 2-level system we have now created would be a basic building block, Audi said. This work is currently very far away from a working quantum computer, but it does open up interesting avenues of research. If scientists can manipulate the 2-time crystal system without destroying its quantum states, they could potentially build larger systems of time crystals that serve as true computational devices. Copyright 2022 Live Science, a future company. All rights reserved. This material may not be published, broadcast, rewritten, or redistributed. Paul Sutter is an astrophysicist at The Ohio State University and the chief scientist at COSI Science Center. Sutter is also host of Ask a Spaceman, Real Space, and COSI Science Now, more by Paul Sutter. Live Science is one of the biggest and most trusted popular science websites operating today, reporting on the latest discoveries, groundbreaking research, and fascinating breakthroughs that impact you and the wider world. More by Live Science. Expand your world with science. Learn and share the most exciting discoveries, innovations, and ideas shaping our world today. Subscribe, sign up for our newsletters, see the latest stories, read the latest issue, give a gift subscription. Follow us. Return and refund policy. About. Press room. FAQs. Contact us. International editions. Advertise. Accessibility statement. Terms of use. Privacy policy. California Consumer Privacy Statement. Use of cookies / do not sell my data. Scientific American is part of Springer Nature, which owns or has commercial relations with thousands of scientific publications. Many of them can be found at www.springernature.com/us. Scientific American maintains a strict policy of editorial independence in reporting developments in science to our readers. Copyright 2024 Scientific American, a division of Springer Nature America Incorporated, all rights reserved.